Welcome everybody to another edition of the SIBA webinar series. My name is Andreas Park. I'm a professor at the University of Toronto. I'm also one of the co-founders of the SIBA Forum together with Fahad and Will. And I'm very happy to welcome Andrea Canidio here today to this webinar series. Just quickly, some housekeeping items before we go into the details. We have the Q&A open where you can ask questions. I will be the moderator for these questions, so that means that I will check if there's any clarifying questions that need to be answered immediately. If not, we have several breakpoints during this webinar series, during the presentation, when we can ask the bigger questions about the background and so on. And I want to encourage you to put these questions into the Q&A so we know what you want to know. With that, I want to introduce you to Andrea Canidio. Andrea is an academic, but who recently transitioned to working for the CowSwap protocol. If you don't know, CowSwap stands for coincidence of wants. And it is actually very remarkable of how much pickup is seen over the last year or so. Now, Andrea will talk to us about it, about the innovations that are coming from this space, which I believe are interesting beyond the specific protocol, but they're in the biggest space of something called intent-based auctions. For those of you who have attended our CTCE conference in the fall, we had a presentation there too. And I think this is probably one of the growth areas, at least in terms of academic research too. Now, I'm a big fan of Andreas' work. It is exceptionally clear. So, you all in for a treat for a very nice and clear, albeit probably technical presentation here. So with that, Andrea, I'm going to hand the floor over to you. The presentation will roughly last somewhere around 45 minutes, and then we're going to have an open Q&A afterwards too. Andrea, the floor is yours.
Thank you very much, Andreas. Thank you for the kind introduction, and also let me thank the organizer for inviting me to present. And let me share my screen. Yeah. Okay. So, can you guys see my screen and hear me clearly?
Yes, it's all good.
Okay, perfect. Well, yes, as Andreas mentioned, today I'd like to discuss with you trade intent auctions, okay? And I'm planning to split my presentation in three parts. First, I'd like to just give you an overview of what those objects are and why they are important. And then I'd like to discuss the most common auction mechanism, meaning these are auctions, and auctions come in many flavors. And we also find many different versions of these auctions in production right now. I'll then highlight some of the issues that exist with current mechanism, and then I'll transition to a research paper that I co-authored with a colleague, Felix Haneke, that essentially tries to, well, first of all, formalizes the problem, does an analysis of the existing auction design, and then proposes a new auction design that tries to address the existing problem. Okay. Now, first part, so what are those things and why are they important? Now, I think as a starting point, we all know that blockchain is permissionless, meaning that anybody can, for example, start a new decentralized market with an innovative mechanism, with its own logic to calculate fees and so on and so forth. But the problem is that, and this is great because there is a lot of innovation, which we don't necessarily see in traditional finance. At the same time, it creates market fragmentation, meaning that now if I am a trader and I want to figure out what's the most efficient way to swap one asset for another, well, I'm actually staring at 10 different marketplaces, all with their own quirks and specificities. So it's very, very difficult to figure out, okay, what's the best, most efficient way to execute a trade. And of course, I could also execute my trade. These are just, maybe there are 10 markets where I can do my swap directly. Of course, I could do my swap through intermediate asset, which further expands the set of possibilities. So there's gigantic complexity, and at the same time, it's also blockchain in general is an environment that can be very adversarial, and in particular, traders who want to swap token, unless they take extra measures, they risk being exploited by malicious actors via what are known as sandwich attack, which I don't think I need to explain too much. Now, and trade intent auctions are a response to these complexities and those risks. So first, what is a trade intent? Now, on blockchain, a trade or a swap would require a user to specify, obviously, a sell asset, a sell amount, and a buy asset, and also a specific AMM, okay, a specific market, a specific execution for that AMM. Now, a trade intent is the same thing, but where you do not specify the execution path. So essentially, you're specifying some parameters for your transaction. The what, you want to swap something for something, maybe with some parameters like a limit price, but you don't specify how. And then there is an entity called a solver. So entities called solvers that compete in an auction for the right to then execute the trade intents, if you want, for the right to complete the trade intents and turn it into actual trade. So really specifying an execution path for your trade intents. And each execution path that this solver might propose generate a price for the trader. And obviously, there are many auction mechanisms, and the details here are important. But for a moment, let me just say that all the mechanisms have this feature that the best proposal, so the proposal that generates the best price for the trader, wins the auction and gets the right to execute the trade. And also important is that solvers in all those mechanisms bear all the risks. For example, the risk of being sandwiched, meaning that when they bid, they propose a price for the trader, and then when they go and execute, if something happened, like they get front run, typically they are still liable to return to the user what they promised at the bidding stage. And I think it's interesting for the whoever is in the audience that is maybe better versed with traditional finance to try to connect these objects to something that might already exist in traditional finance. Now, the first one is that I think there is a similarity between the relationship between in blockchain, what is a trade and a trade intent, and what is in TradFi sometimes called parent order and child orders. Parent order will be a situation where maybe an institutional trader will go to a broker and say, hey, I have so many millions to trade. Please buy or sell X many millions of this asset. Perhaps specify some parameters. Okay, you have to do it before a deadline or this and that. And then the broker will take that and produce what are called the child orders, which are actually the execution of those orders. So we'll say, okay, well, I can sell this much in this market, this much in this other market, and maybe wait a bit and all that. So in a sense, there is a relation, trade intent and trade are related in a similar way.
I'm going to just butt in for a moment.
Sure.
So actually, I think a better analogy here would be that of what's referred as a liability desk. So a liability desk is where you pick up the phone, you call a trader, and then they take in your entire order. They have to give you a price, and then it's on them to afterwards, trade against the order that they took into their inventory. So it's called liability because obviously you take a liability as a trader.
Okay, cool. Yeah, it's like all ways you can think of in which this object from DeFi actually relates to existing things, they are great. So liability desk is another one. Now, to me, the second one I wanted to discuss. Yes.
I will also say this actually. So this is for the benefit of the entire audience. I think actually the analogy is there, but it's not too strong, which makes it actually very interesting for us as researchers, right? Because I think this is actually generally very novel because liability traders and all of these broker relations are not really a bidding process, right?
Yes, exactly.
Go to a trader, right? So.
Yeah. So this is for the relationship between trade and trade intents, but of course, in the liability desk or this typical parent order, child order relationship, there is no auction. Now, the other bit that I think is related to something from TradFi is the proposal from the SEC from a few years ago of having exactly this order by order auction in case of retail flow from, for example, Robinhood. And that was discussed, and there has been a bunch of, debate. But it's something that has not been implemented, but has been discussed in traditional finance. I see raised hands.
Well, standard practice would not have people ask questions in the interim, but if you want to, you can take Robert's question.
Yeah, please, let's take it.
Okay. I allowed you to unmute yourself. Hold on. You should be able to talk, Robert. Does this work? Robert, if you want to ask a question, you would have to unmute yourself. Okay, not asking the question, so let's move on then.
Maybe we can keep it for later then. So anyway, yeah, so the closest analogy is that with this proposal by the SEC that, however, never took off. I mean, it's been discussed but not implemented. Yeah, so this has not happened, unlike trade intent auction, which instead are very much in production, alive and kicking and quite important. In particular, this is like data from the last 3 months that is only about Ethereum. By the way, today I primarily focus on Ethereum, but trade intent auction exists in many chains. There are maybe slightly different protocols that are present depending on the chain, but yeah, it's still the most activities on Ethereum. So let's just zoom into that case. And as you can see, in December, the total volume of this trade intent auction was about 12 billion US dollar. In January, it was a bit high, a bit above 10 billion. In February, it was a bit less than 10 billion. But anyway, we have, unlike the traditional finance equivalent that was proposed and never implemented, this object here is in production, is working, is intermediating a lot of volume. And in particular, there are 3 protocols that are the main players in this market. One is Cow Protocol, the organization for which I work, that in February, this is the blue bar here, so in February intermediated 6.9 billion. 1inch Fusion, that is the gray bar, and Uniswap X, that is the orange bar here. I also thought that another characteristic of this trade intent auction is that you can exchange any asset for any asset. I mean, it's not like the stock market in the US where essentially everything is exchanged for dollars. There are markets that are really many to many. And in this sense, another analogy to the traditional finance is with Forex markets or perhaps FX desk of a bank whose job is precisely to route orders from different clients that may need this currency or this other currency. So yeah, so there is this analogy, but there are also very important differences. The first one is just the number of assets. So according to Wikipedia, there are apparent about like 100 different national currencies, some of which are very obscure, like the Saint Helena pounds or things like this. So concretely, on Forex market, I think there are about 80 currencies that are exchanged. Well, in trade intent auction, the number of assets is just much, much larger. So I ran a query just on Cow Protocol because for me it's easy to do. And on the different asset exchange last month, so not in the entire history, but just last month on Cow Protocol, and it was like 2,137. So way more. And of course, here the subject is asset pair. So I mean, there is just order of magnitude more complexity in trade intent auction than on Forex markets. The other difference is on the distribution of volume on token pairs. In Forex market, the top 5 pair account for about 65% of the total volume, and they all involve the dollar. Whereas, again, just looking at Cow Protocol, the top 5 pair account for about 25% of the total volume. So I mean, there is a much longer tail in the trade intent auctions. And on Forex market, like all assets are the same. They're national currencies. But on the blockchain, like these assets are and tokens and cryptocurrencies are programmable money. Okay, so they can be very heterogeneous. Some assets might need special operation, might need to be wrapped or unwrapped, might trigger certain events. So there is really a large heterogeneity in the type of asset that are traded. And then on top of that,
can I interrupt you for one more question?
yeah,
Sorry.
absolutely.
because I think it's kind of for the motivation is probably important. So, I mean, one of the things that people often say is the topic of fragmentation, right? So,
Mhm.
in also in crypto, like fragmentation is different systems and so on. But A, we have aggregator protocols, and B, here it just seems that you have actually access to a lot of different pockets of liquidity that are put together. So that seems to be in contrast when you have a market like an OTC market. I think Forex, I'm not sure to what extent Forex is OTC, but probably a lot of it is, right? Where it's pretty difficult to piece together if you want to go from, I don't know, Singapore dollar to I don't know, to what is it, the Danish krona. That's probably a multi-hop process, which can be quite complicated. You can do all of this in crypto or on the blockchain. You can have one solver aggregate everything for you, right?
Correct. I mean, the solver itself then might then have to do all the extra hop that you were describing, but it's somewhat abstracted away from the point of view of the user and is delegated to these professional entities that are then competing to each other on who can perform those steps the most efficiently.
So really fragmentation, if you ask me, so fragmentation in the blockchain space seems to be lower than probably in traditional finance.
Yeah, I
Can
mean,
we say?
it's perhaps because I think if before those things existed, maybe the fragmentation was higher, and because of that, there are these new pieces of the stack that allows to perhaps now, as a result of the introduction of those auctions, an even smoother user experience than in traditional finance. Yeah, but I think it's an extremely valid point. Yeah, and then last but not least, I mean, in this trade intent auction, I mean, I don't know how often new national currencies are introduced, but on the blockchain, like new stuff come online all the time and can become very important in the space of a very few months. So that's also why those auctions are more complex than the forex market or the operation of a forex desk. And yeah, I mean, there are many interesting data that one could look at, and I thought that this could provide some interesting insight, a bit of flavor of what's going on in these auctions. Again, this is from Cow Protocol, is from the last 30 days, and it's a distribution of volume by token pairs. This is 24 token pairs, and it's about 50% of total volume over these 30 days. And in a sense, if you look carefully, you will see three classes of assets. There are USD pegged stable coins, but again, with different types: USDC, USDT, USDE, PyUSD, so USDS. So which you can argue they're similar but not identical, including their interest, so yield-bearing version, so the one that generates an interest for the owner. It's all mixed up. Variations on the US dollar stablecoin, variation of ETH, wrap stake ETH, wrapped ETH, and so on, and then Bitcoin. Okay, so if you want, there are dominant assets in this market, but there are many variations of these assets, and they're not exactly the same. And in fact, if they were the same, people wouldn't want to swap one for the other, right? So that's kind of people have preferences over those assets.
So I think this is quite remarkable if you look at the distribution. A lot of this is stablecoin to stablecoin, right?
Yes.
Do you have a sense, is this because your mechanism does a multi-hops process where they basically look at some pairs are traded USDC, others are traded with Tether, and then they're trying to use that as an interim step? Or is this because there's a genuine interest in swapping these specific stable coins for one another?
I think there is a genuine interest. Remember that if this was instrumental to do some other swap that you may want to do, but okay, there you need to go through this intermediate asset. Here, the user doesn't have to do it. It's the solver that will figure out that, okay, well, to do random token A to random token B, I have to go through whatever, USDC ETH or USDC USDT. So here is really the preferences of the user. And so, yeah, I mean, people have preferences over USDC, USDT, change these preferences. So sometimes they sell one for the other. in a way that, I mean, I cannot fully explain, except that, you know, yeah, I don't know. I don't want to get into discussion because I'm not too sure either, actually.
Yeah.
All right. Yeah, so this is what those objects are. Now, these are auctions, so there are different mechanisms. Actually, this may be the point to pause if there are questions.
Right. Other than mine.
Yes.
Yeah, so
But if
are
you
there
have
any
questions.
questions? If you have questions, you can put them in the Q&A, or we can try another round of raising your hands. Maybe one question would be, so if you have, oh, okay, Daniel asked, how profitable is it for the solvers?
How profitable it is for the solver? Okay. This really transition to the different mechanism because the probability of the solver will be generated in different ways depending on the mechanism, which is actually not something I was planning to discuss. But for example, in Cow Protocol pays solvers, and the rewards earned by solvers are the difference between the value they generate and the value generated by the second highest bid, by the second best bid. So it's this delta which is in one way it's a reward to attract solvers and attract competition. And another way it's also a way to get around the famous Milestone Sarthur-White, I always mispronounce it, theorem, because of the subsidies, solvers can participate into the game without strategizing very much on how to bid. Okay. Whereas the other two protocols, Uniswap X and 1inch Fusion, they don't subsidize solvers at all. And so now solvers make profit, like in any auction, by misreporting slightly. You know, they can generate 10, but they were going to bid 9. And if they win the trade, they're going to have 1 as profit.
So then we have Han Chen has raised his hand. I have permitted you to talk.
Thanks. Hi, Professor. My question is that I noticed that you said all the risk will be taken by the solver side. I think mainly because the user will need to submit an order and wait for the solver to execute that on chain. I'm wondering, would this like introduce higher fees on the client side because the solver will cover the risk, but the cost will like just go to so the solver need to charge the clients more.
This is very much the argument for that came out in this like the TradFi version of this auction. So the solver are competing with each other, and one dimension of the competition is how efficiently they can generate those trades, they can produce those trades. So their scoring includes the price that they generate and every other cost that they might incur. So it's really about, you know, a solver should be able to do better than a random user by himself because it's a professional party. And this is then also shows up in the way you score the solution submitted by solver because it's going to include every cost that you are trying to push on your user.
Thank you.
You're welcome.
So Fahad and I had a question, which is, so when a solver wins the bid, how do you enforce commitment from the solver?
Yes, so it's a tricky question in a sense that there are different models, and there are so there are essentially two things you need to worry about. The fact that let me just say, in all those systems there is an on-chain guarantee that the solver cannot make someone trade at a worse price than the slippage tolerance implied by the trade intent that the user submit. So that's kind of, as usual, you cannot violate a user slippage tolerance. But of course, you know, say slippage tolerance is, okay, I want to sell at a price that is no less than 10, but in the bid, the winning solver promised 12. It is possible that the solver then delivers 11. Okay, that's at least on Cow Protocol is a slashable offense. The solver gets slashed. There is, however, a second event that, in my view, is trickier to handle, which is a revert, meaning that the solver goes an execution chain, and then something happen, and many things can happen, and that are not necessarily under the control of the solver, and the transaction just never land on chain or reverse or whatever. In which case, the user gets to keep their money, and the trade just never execute, and it's put back on the order book. Now, in this case, the solver has a penalization, and we start again. This, however, is tricky because, yes, reverts can occur in many cases for reasons that have nothing to do with the solver, but can also they can also happen for strategic reason, and that's where you have to the mechanism design matters, because a solver might strategically revert when prices move against him, but from the time it bids and the time it actually should be executed. So it's a bit of this is a tricky case. For the moment, I mean, at least on Cow protocol, there is a punishment for a revert that should take care of those cases.
So just to be clear, right? So and so everybody's clear on the mechanism. So the idea is you make a bid as a solver, you win the bid, and then you execute. So it's not. So this is where actually my analogy earlier on with the liability traders is wrong, right? Because in liability trader they actually have to take it. They actually have to give you a price, put it in inventory, and so they're on the hook for it. Whereas you solvers essentially are just trying to say, well, I can actually do a good job for you, and here is how I execute it. And then you basically, as the individual, still see all of these different split in the swap coming through. Is that correct?
So that's correct, but there is also the model in which a solver uses his own inventory, because I can also solve by saying, look, I have a pot of ETH and USDC there. Let me just quote you a price and then use my money. So it is quite correct, but it's all integrated in one big auction in which solvers can compete in many ways.
Okay. So then
this is a great way to transition to what are those mechanisms, okay? Because we actually started discussing about that.
Yeah, I know. But and on this one, I just want to go through quickly that there's there's 3 questions in the Q&A. So the first one is about whether or not the solver bids are public. And because if they are, then there should be some collusion issue. So maybe you come to that when you talk about the auction. If not, then you can maybe address it.
So collusions among solvers?
Yeah, so if you make the bids publicly available, so there's a process by which you can see how they bid for it. I think the argument is if you have a repeat common value auction, right? So then you can have collusion. Right?
Yes, okay. I can address it. Okay, maybe let me take this for when I discuss the different mechanisms.
Okay, so then there's 2 more questions. So the first is, what factors drive price discovery here?
Price discovery? The solver's job is to look at the market and figure out what is the best prices.
And then the last thing is, Alfred asks if these swaps are atomic or if there's any kind of settlement risk.
They are atomic. And so if anywhere if a solver proposes to solve some orders by accessing multiple AMMs and then returning the money, if anywhere along the way the solver does not get what he was expecting, okay, the solver might decide to chip in some money. Okay, that's another way because I don't want to be punished for the revert. But in the end of the day, it needs to produce what he promised. And if he doesn't, everything reverts. So it's atomic in a sense that you are going to just go back as if nothing has happened.
Okay, well, this is a great discussion so far. So, but I'll ask you maybe now to move on to the next part.
Okay. Now, yeah, so I think when in these auctions, there are really 2 forces at play, okay? One is because we discussed there are many assets and even more asset pairs, there is scope for specialization. So in fact, there are different ways to be solvers. Like there are some solvers that either collaborate or are market makers. So essentially they operate like by quoting with their own money. But then, and this might work well for some token pairs, there are other solvers that are more like very sophisticated optimization algorithm to access on-chain liquidity. There are other solvers that it's all about optimizing gas for tokens that require special operations. So, I mean, there is many ways to be solver. So specialization is important. At the same time, it's also important to be able to exploit complementarities between different trade intents that might be auctioned off at the same time. First of all, in general, swapping on an AMM, the gas that you pay is independent on the volume of the trade. And so if you have trades that trade the same object, or perhaps in some intermediate hop of the trades, it makes you gain efficiency by putting them together. There could be coincidence of wants, for example, where you can have direct peer-to-peer trading. This direct peer-to-peer trading may emerge in some intermediate leg of a complex execution. So you can exploit complementarity between trades. And it turns out that the three protocols that I mentioned earlier chose different mechanisms that are trying to essentially gear more toward like the specialization or the complementarities or exploiting complementarities. The first one is Cow protocol. Cow protocol runs a multidimensional batch auction, which I'll discuss in a few seconds, more in detail. And it's very much about exploiting complementarities. 1inch Fusion runs an order-by-order Dutch auction. And Uniswap X runs a order-by-order hybrid auction that has an element of a Dutch auction, but also a quoting competition that I also discuss in a second. But those two things are really, because they're order by order, they're separate auction for each order that comes in, are really mechanisms that have, in my view, more the solver specialization in mind. So more in details about those mechanisms, the multidimensional batch auction by Cow protocol is one of these interesting cases where I know that people read the paper by Budish, Crampton, and Shim, and from that they started thinking, oh, what could be a good mechanism to set up this trade intent auction? Now, so it is inspired by that. It turns out to be still quite different from the batch auction in that paper in many respects. The first one is that here is a batch, is a collection of trades that might have nothing in common, meaning there could be like one trade ETH USDC and another trade random token A, random token B. As long as they arrive more or less at the same time, they will be put in the same batch. Whereas in the paper by Budish, Crampton, and Shim, a batch is like on one market. So a batch contains order only selling or buy a specific asset. So that's one difference. And then there is communication with the solver where you are going to expose to them, okay, these are the orders that are on the batch. Then each solver proposes prices for the trades on the batch in a way that is private. So other solvers don't see that. It's a private communication with it's an off-chain, it's a server, okay? And again, this is different from Budish, Crampton, and Shim in the sense that here there is a very explicit bidding. So it's a more like a very explicit auction. Solvers have to submit something and to the auctioneer. And again, how they produce those prices is up to them. They can use their own inventory. They can just optimize the available public liquidity. They can use other orders on the batch. Okay, they can just say, hey, I can combine the orders on the batch so that everybody is happy with the liquidity already on the batch. Or more recently, they can also access what are Cow AMM pools, which is a new type of AMM that is exclusive to Cow protocol's batch and comes from a paper that I wrote with Robin Frisch a couple of years ago, which itself tries to figure out how to adapt the Budish, Crampton, Shim idea to the case of DeFi, let's say. And then, and then was obviously with some adaptation turned into a product, and now it's been up for a few months. The main rule is uniform clearing prices, like in Budish, Crampton, and Shim. So if you have two tokens trading, especially in the same direction, two orders trading the same tokens, they will have to have the same price. And the ranking of solution is based on the total value returned to the trader and to the Cow AMM pools. The Cow AMM pools, the LPs are also participants in the protocol here. Note that this requires an external price vector because you may be comparing a solution that returns 10 units of a token to a solver, to a user, and some other amount to another user, to another solution. But there could be, those will be apple and pear. So you need the price to make them comparable. Okay, this is the multidimensional batch auction by Cow protocol. Now the other two protocols, they are order by order auction. The 1 by 1 inch is a fairly straightforward Dutch auction in a sense that when an order comes in, the protocol parameterizes the Dutch auction by setting up a starting price for the auction. And there is a variable decay. It's kind of goes fast when you are away, when you're farther away from what should be the market price. It goes slowlier when you are near the market price. It allows for partial fills. And 1 inch started as a routing algorithm, so as a routing service. And this routing service is still embedded in the auction as a sort of reservation price, if you want. And yeah, so this is, let's say, simpler to explain. Whereas Uniswap X is a bit more complex than that, because it has really a two-step process. First, there is a quote competition where the protocol will expose the order to a bunch of solvers, and they will propose a quote. And here, the best quote wins, okay? Now then, the winner of the quote competition has exclusive access, exclusive right to execute this trade for a specific window of time, past which the Dutch auction kicks in. And then at that point, there is a usual decaying price decreases with time, and the first solver that raises its hand can get the order. And the Dutch auction part is off-chain or on-chain, depending on the network. And Siamak, I don't know if it's correct, but he has a nice paper when, possible issue that arise when this is done on-chain, because, you have these discrete jumps, and then what happens if the real price is in between? People will rush and create an EV, so on and so forth. And this is also integrated with the Uniswap router. Okay, so again, zooming out a little bit from all these details, there are really like two models here. One is an order by order auction of various flavor, but the point is that each order has a separate auction. And the other one is like the batch auction, multidimensional batch auction. What is the high level difference between those two models? Let me illustrate it with an example. Suppose that I have two traders that sort of show up more or less simultaneously. One that wants to buy 1 ETH for USDC, and the other that wants to sell 1 ETH for USDC. Now, what happens if I have this order by order auction? Well, I have two separate independent auctions in which each solver will assign some probability of winning each of the auctions. And for simplicity, let me assume that solvers don't have any inventory. Then they are forced to solve using publicly available liquidity, because with some probability they win only one order, and if they don't have inventory, this one order, they can solve it only with access into some AMM. Which means that in this case, the best possible outcome for a trader is that the one that buys pays this P buy, and the one that sells receives this P sell price, where P buy and P sell are essentially the best possible buy and sell price that are available on chain in the ETH market, like ETH USDC market. Okay. So the outcome of the auction is determined by the best buy and sell price available on chain. Now, in a batch auction instead, a solver is able to use the available liquidity. So one order has liquidity for the other. And so you get a save on gas fee, on external market fee, achieving much higher efficiency. But this is not without challenges. And in particular, there is one important challenge, which is, okay, now I can do better than the order by order auction. And ideally, I would like both traders to benefit from these additional efficiencies. However, solvers don't really have an incentive to be fair in any way, because they're just scored on the total amount that they deliver, not on how this is distributed. And at the same time, it cannot even be the auctioneer job to make sure the solution is fair, because the auctioneer doesn't know this P sell and P buy. They doesn't know what would have been the outcome of this counterfactual in which we are running two separate auctions instead of a batch auction. So the problem with batch auction is one in which you are able to achieve higher efficiency, but you don't really know how you should share this. So to summarize, therefore, like batch auctions are clearly better at exploiting complementarities between different trades. Now, order by order auction are also better. Okay, it wasn't in my example. Whenever you have very specialized solvers, because okay, now you can assign one order to the solver specialized in that order, another solver in the other order to the solver specialized in this other order. And at the end, batch auction are also problematic in a sense because they can be unfair. And it's difficult to guarantee that everybody benefits from the efficiency from batching. Now, the way this is handled currently at Cow Protocol is through something that is called eBBO test, inspired by the national NBBO, which essentially is an algorithm that the protocol runs after the auction has occurred and checks whether everybody received a price that is at least as good as some sort of routing algorithm that we maintain, which is, however, a bit okay. It's a big overhead for the protocol to maintain this, and it uses the knowledge of the protocol, while in fact, ideally, you will want to know from the solvers what would have been a reasonable execution for each order individually. And so in some sense, the open question that allows me then to transition to the research paper is, okay, can we think of another mechanism that can result either in batching or specialization, depending on, whether it's more beneficial to, so what is most efficient to do, and has some sort of notion of fairness or fairness guarantee embedded in the mechanism.
So can I ask for some clarification there? So the order by order is relatively clear, but the batching sounds to me like something which is, it's like, you allow the individuals, so the individual participants in the auction to batch together pieces. Because my understanding of batch auctions usually is, I mean, maybe this is naive, but I thought always an auctioneer first batches, and then there is a way to assign whatever imbalance exists, right, to somebody else, right? So somebody else has to absorb the remaining liquidity. Actually,
Yes.
maybe that's not the right way to put it, but that's kind of the idea of, say, a Kyle-style auction, right?
Yeah. Yeah. So I think
Or
because
market maker auctions,
you
maybe a
read
better way to.
the Buddhist the paper I was mentioning earlier, here is slightly different. The auctioneer doesn't do anything, and the task of spotting that you could in fact match one order with the other and at what price is delegated to the solver. Because here is an easy case, of course. Yeah, we can think of an algorithm that spots this, but in general, you could have one order wanting to trade ETH USDC, another USDC for RAT Bitcoin, and a solver can do just the RAT Bitcoin ETH leg of the trade and allow some sort of a ring trade with accessing minimal amount of liquidity. There are all sorts of variations on, there are many type of cows, if you want, of coincidence of ones that you can think of. And of course, you have like ring trades. The problem can become very complex when you allow for multidimensional batches. That's the point, because here you could have like 3 trades and you can do a ring if you want. So spotting the possibility of doing this is left to the solver, and the solver therefore has to announce how they want to source liquidity and the prices that they can propose.
And so Gunnar asked that question, is there anything of some form of optimality and in particular from some perspective, welfare optimum or so? I remember there was a discussion in the old days about treasury auctions, right? Of whether or not you should use a uniform price one or a discriminatory one, which is in some sense there has a certain flavor here too, right? Is there any sense of on optimality?
Optimality.
Most likely not. Just wondering if this is something that.
No, I'm sure I can reduce the problem to for example, let's assume technology is fixed. So solvers have their own algorithm that produce something and their own methods. And then the problem is just eliciting this from them in a way that creates the least distortion. Yeah, hard to say, because really then we get into the Myerson Satterthwaite problem of is there even can we really achieve efficiency in any of these two-sided markets? Yeah, let's complex problem. Let not.
I'm going to stop asking questions. There's some more in the Q&A, but I'll come to those later when I interrupt you more.
Okay. Right. So I can transition to the research paper where we propose this new.
Oh, okay. So since you have, can I just ask a few questions?
Absolutely.
Right. So I think Jaime asked a question, which essentially is a question of, which is sort of something that's come up in DeFi recently a little bit, which is that is there any inside information? So is it possible that is there a concern that some solver could have access to more information than others by having a view of the server or the like? Or is there any mechanism that prevents that from happening?
So there is concern about the solver being able to exploit the knowledge of what orders are on the order book, because the protocol needs to expose those orders to all solvers in order to collect bids. And a losing solver might then, solver might then resell this information to other actors that may have some sort of more trying to do some, these are called non-atomic sandwiching. This has been discussed and it is a concern. I find it a little bit, it's an overblown concern in my opinion, but I mean, the theoretical possibility is there. Other type of insider information, it's hard to say now. These are an auction, so each bidder has its own valuation of the object, has its own ability to generate the buy asset from the sell asset, and the auction should generate information. And if there is someone who's very, very well informed and is much better than everybody else, is going to be able to extract additional rents, like in information rent, like in any auction. So I'm not too sure I see this as a particular problem.
And then I have one question from Siamak, and I'm going to combine that with something that Fahad asked me, which is, so, in CowSwap, you have essentially, it's a coincidence of ones, right? So can you give us a sense of what the extent of it actually, so how much of batch auctions have this coincidence of ones on both sides? And that probably is also a question which comes to Fahad, will ask me about the frequency of the batching. So what's actually the frequency of these auctions that we're talking about? Are
The
these endogenous?
frequency,
Is it fixed schedule?
yeah. So there is an element of endogeneity in the sense that so in practice, what happened is that there is an order book, because people can also submit limit orders to Cow protocol, or orders that cannot be immediately executed, and they will sit on the order book for the time specified by the user. And there may be periods in which there is no order coming in, no executable order. And the protocol has some heuristic to figure out, okay, all orders are so far from the current market prices, we don't even run the auction. Okay, that's one case. Then if there is some order that is in the neighborhood of what's the market price, so it could be executable, the protocol then initiate the auction. And currently it's a bit kind of the auction itself. So announce the orders on the batch, receive the bid, give times to the solver to calculate, receive back the bids, is a bit longer than an Ethereum block. It's a bit longer than Ethereum, and there is a whole work plan to bring it just in line with the Ethereum block, so that you can run the auction in a block and then execute in the next block. Okay, now how thick are the batches? So the batches are now so the average number of trades on the batch is 1.5 something. So we have a lot of batches of a single order, and we have also some batches with multiple orders. And the straight coincidence of ones, like one guy trading with another guys, are very rare. They're indeed very rare. But in general, the fact that you can have additional efficiencies by putting two trades together in ways that can be very creative, I'll argue that that happens more frequently. Just in terms of, for example, gas savings. Know that now all the, like Fahad has this article on Uniswap v4. Uniswap v4 is one big smart contract over all the AMM sits. And that's exactly the type of architecture that creates additional efficiencies from batching, because now, again, I can touch the AMM only once for a bunch of trades that may be completely unrelated, but this is just one operation on the AMM, and this generates additional gas efficiencies. So yeah, direct cows are rare, but efficiency, gas efficiency, other type of efficiency, they emerge more frequently.
Okay, thank you. So I want to be mindful of time and not derail your talk any further. So go on to talk about your talk with Felix Henniker. Yes,
okay. So yes, so essentially, I don't think I need an introduction for this talk, because it's precisely, can we find this better mechanism? And the way we go about in this paper is through like 4 steps. The first one is, okay, well, we formalize the problem in a way that a game theorist will understand. And the key assumption is a combinatorial auction model where there is a new assumption, which is a feasibility constraint that obviously I'll introduce in a second. Then, yeah, so far I talked about fairness in a fairly intuitive way. Oh, there is this other mechanism, the auction by auction, order by order auction, and we want the batch auction to be fair relative to this other mechanism. This is by itself new because it's not really a notion of fairness that is already present in the literature, okay? And so we formalize it. We formalize what it means for a mechanism to be fair relative to another mechanism. Then we use this machinery to study batch auction and order by order auctions. And the result there is that batch auction generate more competition than order by order auction, but they can be unfair. The unfairness is exactly the intuition I gave earlier. The fact that batch auction generate more competitions come from the fact that, sometimes you have specialized solver and therefore only a subset of solver compete when you have order by order auction, but when you have a batch auction, all solvers are competing with each other all the time. So there is a higher level of competition. And finally, the more meaty part of the paper is to propose this new mechanism, the fair combinatorial auction, that is a combinatorial auction. So requires solvers to submit multiple bids. In particular, solver will submit bids on individual orders, which a bid on individual order will mean, okay, if I only win this order, this is how much I'm going to return to this guy. But also bids on batches, so on groups of order, which will mean, okay, well, if you give me these 3 orders, this is what I can give back to this guy, this guy, this guy. Now, the mechanism uses the bids on individual orders, on individual trades, to generate a reference against which to talk about fairness. In particular, it's going to look at all these individual trade bids and then calculate what would be the outcome if we had run several order by order auctions with those bids. Okay, and those order by order auction can be many type of auction. In the paper, we look at the case in which they are in first price or in second price. Okay, so essentially look at only the individual trade outcome. Think of this as just several simultaneous order by order auction. Calculate the outcome and use that as a reference for fairness. Then you use this reference to filter out batch bids. If you eliminate those batch bids that are worse than the reference outcome for at least one trader. So you are going to end up in a batch only if you benefit relative to this reference outcome. And then, okay, you choose the winners among the surviving batch bids and the individual trade bids. Okay. Now, in a sense, this fair combinatorial auction is a bit of a mix between having individual order auctions and batch auction, like it's sort of one on top of the other. And that's correct. The thing is, you should not think that the equilibrium is going to be a convex combination of the two. It may look very differently because by putting everything together, we generate some novel strategic considerations that determines the equilibrium. And in particular, the point we're going to make is that not all fair combinatorial auction in equilibrium provide fairness guarantee, but some do. So there are some combinatorial auctions that do provide fairness guarantee. Of course, I'll be a bit more specific when I show you the results of the model. Excuse me. Yeah, the model is I would say, at least the simple version of the model is quite simple. Then it can be obviously made more complicated. But there are 2 traders. Trader 1 wants to sell 1 unit of token A for token B, and its utility is just the amount of token B that it receives. Trader 2 will sell 1 unit of token C for token D, and again, its utility is going to just be the amount of token D it receives. There are then 2 solvers. Now, solver 1 is specialized in trade 1, and what it means is in the next slide where I discuss the technology available to those solvers. Similarly, solver 2 is specialized in trade 2. Solver's objective is just to maximize the value of the asset that they hold at the end of the game. And for this, they see some notional market price for asset D in units of asset B that they use to calculate the utility at the end of the game. And For the talk, let's say they have no inventory, but the paper considers inventory. So everything I want to say extends to the case where there are inventory. And then to the solver technology, when I said that solver 1 is specialized in order 1, means that if solver 1 is matched with order 1, it's going to produce beta unit of token B, where beta is drawn from a distribution between beta lower bar and beta upper bar. Whereas if solver 2 is matched with order 1, it's just going to produce beta lower bar unit of asset B. So beta for solver 2 is always worse than solver 1 at trade 1. And the reverse is true for trade 2, meaning that if solver 2 is matched with order 2, it's going to produce this delta unit of token D, where delta is drawn from this distribution. Whereas if instead if solver 1 is matched with order 2, it's going to produce the lower bound. And so solver 1 is always worse than solver 2 at order 2. And then there is this element of complementarity, which in the model we captured by introducing the parameter G that says, okay, look, if solver 1 is matched with both order, it's going to produce G times beta unit of asset B and G times delta lower bar unit of asset D for G greater than 1. So G is a bit scales up everything up by some amount, okay, because you can generate additional efficiencies by having both orders. And same for solver 2. And the parameter, yeah, there is delta, beta are drawn at the beginning of the game, IID, private information. G is a parameter known to solvers, but not to the designer. This is simply to avoid cases where the designer can condition the exact mechanism it implements on G. Say, I mean, the mechanism cannot be a function of G. That's another way of saying. Yeah, and the mechanism is also fairly straightforward since it's a combinatorial auction, meaning solver will submit 2 bids, one for each individual trade, with the interpretation I was mentioning earlier, which is an amount of token B that the solver is going to return if it wins only the order 1, an amount of token D that is going to return only if it wins order 2. And then each solver will also submit a batch bid, which is 2 numbers, amount of token B to return and amount of token D to return, in case the solver wins both orders. And the mechanism determines the allocation of trades to solver and payments, which are like you have 2 payments, one in asset B and one in asset D, from solver to traders as a function of those bids. Now, as I announced earlier, there is this key assumption that it is a feasibility constraint, which says it's a way to capture a form of illiquidity, if you want, that there is no perfect market out there that you can exchange B for D assets as you want at the notional market price. And in particular here, the assumption is going to be, okay, slightly stronger, that says that solver cannot exchange assets after the auction outcome is determined. So meaning they produce some assets and that's what they can return. So for example, if I look at solver 1, I just said that if solver 1 wins only trade 1, is going to produce beta of token B and nothing of token D. Well, this is the most that the guy can return. So there is no ex-post exchanging of asset afterward on the market. And well, similarly, if solver 1 is matched only with trader 2, it can return at most delta lower bar of asset D, but nothing of asset B. And then it's the same if it matches with both trades, okay? So the technology I was discussing earlier binds what the solver can return. And okay, note that feasibility also, so this assumption can also be turned into an assumption about mechanism. We can talk about non-feasible mechanism. Particularly, it turns out that VCG is not feasible in this context, okay? But okay, this is an interesting note, and if you want to know why, you should check the paper. Now, results, okay? Now, when it comes to comparing simultaneous auctions versus batch auctions, so simultaneous order by order auction versus batch auction, we kind of find again the intuition I was discussing earlier. Now, the feasibility constraint, when we look at simultaneous auction, the feasibility constraint means that the worse solver at each trade can at most bid the maximum that it can produce. So solver 1 can bid at most delta lower bar for trade 2, and solver 2 can bid at most beta lower bar for trade 1. Now, the other solver knows that, so the strong solver knows that it can win only by outbidding the weak solver, which means that in equilibrium, we have specialization, and each trader receives what the worst solver at that order can produce. Okay, so trader 1 receive beta lower bar and trader 2 receive delta lower bar. In the batch auction instead, by the way, this is a batch auction which pay your bid, so what the solver announces is what it needs to return. We can show that in the batch auction always generate stronger competition so that the total value received by trader always exceed the value returned to traders in these two simultaneous auctions. And at the same time, the batch auction can be unfair. Okay, this is just in terms of set of equilibrium of the auction. There are equilibria in which trader 1 may receive less than beta lower bar, and equilibria in which trader 2 may receive less than delta lower bar. Now, the most interesting case is the fair combinatorial auction, where we construct the reference for fairness by using a first price auction. Okay, remember the notation here. We use QB and QD, a small q to indicate the bids on individual orders, B for the first order, D for the second order, and the batch bid is capital Q. And because the reference is constructed using a first price auction, the reference for fairness is in fact the max of the, so these two numbers, the max of the two bids, individual bids on first order, and the max on the individual bids on the second order. Because if this was simply two simultaneous auctions, this would be what the traders would receive. And now we have the filtering stage. The filtering stage says that now I want to compare the batched bids to this reference outcome. And the first possible case in which both batched bids gives to the two users more than the two reference outcomes, in which case both batched bids survive the filtering and the auction is then equivalent to a batch auction. So case 1, we fall back to the batch auction. Case 2 is one where one batched bid survives the filtering, but not the other. Okay, one batch bid turns out that delivering less to at least one of the two traders than this reference outcome, so it's excluded from the auction, while the other ones survive. Then the outcome is going to be that is going to be batching by the solver whose bid is not being filtered out. And finally, there is also the case in which both batched bids are filtered out, and therefore the auction then reverts to two simultaneous first price auctions. Okay, just for those of you who have worked in auction theory, here I'm be very loose when it comes to what happens when there is equality. Like in auctions, oftentimes how you break ties matters tremendously for the existence of equilibrium. It turns out to be the case also here. I just don't want to discuss it in this presentation. In the paper, there are all the details of how you should break ties so to make sure that the equilibrium exists. Yeah, okay, all this to say, this is the auction. What happens then? Well, there are additional strategic considerations because now, if I'm bidding in this auction and I need to think, oh, how I'm going to set this individual trade bids? Well, I'm going to probably want to bid higher than in a standard first price auction, because now I anticipate that my bids on individual trade will matter for the reference outcome and might end up filtering out my opponent batch bid. Okay, so I'm trying to kick out my opponent from the batch part of the competition. Okay, so higher individual trade bid. At the same time, if I expect my opponent to be batch bid to be filtered out, I have an incentive to lower my batch bid because, okay, if he's filtered out, my batch bid is the only one, so I can leave it. So in some sense, in this game, there are these two additional effects that come in. And then as a result, we have that in equilibrium, trader 1 receives at least G times beta lower bar and trader 2 receives at least G times delta lower bar. So both traders receives always strictly more than in the corresponding benchmark case that was having just two separate auctions, okay? Precisely because of the first effect here. At the same time, the total value returned to the user might be lower than a straight batch auction, okay? So I may be delivering less value. And so this auction is able to generate fairness guarantees because I can say you are all going to be better off in this auction than this separate individual auctions, but at the expense of value returned to the users. And yeah, I mean, you can map the different regimes that emerge in this equilibrium as a function of the parameters. I unfortunately don't have a lot of time left, so I'm going to go on. Yeah, the other interesting case is the one where it's again a fair combinatorial auction, but where the reference for fairness is a second price auction, which formally is the same as before, except that the reference for fairness is now the minimum of the two bids on the individual trade. Because the second price auction, what determines how much each user receives is the second highest bid. Okay, so I use the minimum where before I was using the maximum. Otherwise, the definition is the same. Turns out that this matters tremendously because when the fair combinatorial auction is built using the second price auction, then any individual bid can be in equilibrium. What is the intuition? Well, if I expect my opponent to bid 0 on the two trades, essentially, I expect my opponent to completely skip the individual trade bids and just bid on the entire batch, then I cannot move. So the reference for fairness will always be 0, no matter what I bid. Okay, and so I also could just decide to bid 0, and we then gonna move directly to a batch auction. Okay, the intuition here is that I have less ability to influence the reference for fairness when this reference is bid as a second price auction, because it really depends on what the other guy is also bidding. And it turns out that the set of equilibrium allocation of this fair combinatorial auction is the same as in the batch auction. So really, this doesn't provide any fairness guarantee. But of course, like a batch auction, it also generates high value to the traders. Okay, maybe this was a bit fast. Let me conclude and maybe take question, and then there is a slide of literature if we have time. But essentially, in this paper, we propose a model of trade intent auctions. We have a definition of fairness that is inspired by cooperative game theory in a sense, because it really looks at what each trader could earn by itself instead of being batch, by itself meaning in an individual auction. And it's different from other definition of fairness because it compares the outcome of a mechanism with the outcome of another mechanism. But of course, this reference outcome needs to be elicited from bids. So there are a lot of these additional strategic considerations that are important here. And it turns out that the details matter because not all fair combinatorial auctions generate fairness guarantees in equilibrium, but some do. And there is a trade-off between these fairness guarantees and the total value generated. I'll pause in case there are questions, and then maybe I'll have time to discuss the literature.
Well, thank you. Let's just start from the back. This parameter G, how should we think about that in practice?
So this is gas savings from having both trades together. Okay. Or, you can use one trade. As I was saying, like it's a bit abstract, but, trader 1 wants to sell token A for token B, and trader 2 wants to sell token C for token D. There is no assumption that those must be different, right? And so maybe, the example I was discussing earlier where sell token A for token B, but then again, sell token B for token C, and then the solver can just do one trade and create a ring. So it's the easiest is gas, but then in practice, how you want to think about this, what those tokens are, there could be other ones.
So then also, a key assumption here in your model seems to be the heterogeneity of the bidders, right? So that they really have complementary or opposing skills in some form.
Yes, here they're very much specialized.
So does the degree of their ability overlap matter in some form, or do they really have to be separate?
No, I mean, to me, the idea is that we want to have a mechanism that can exploit the degree of specialization of solvers. and that might generate specialization in equilibrium if the benefits from specialization is large relative to this G parameter. And so in a sense, we do want to have, so it's relative, right? Because the point here is the benefit for specialization that comes from this parameterization where there is a draw from a B, but the other guy is worse, but then it's G really parameter that determines specialization versus benefit from batching. And
So the reason
yeah,
I'm asking is really the contrasting point would be one where there's perfect competition, right? Where they could all bid, right? And so I'm just trying to understand what the role of the heterogeneity is and the level of competition, right? So as in non-competition. Because if they are heterogeneous, right, and you would do it batch by order by order, you would have, one would be essentially a monopolist, right?
Yeah. Okay. Yeah, correct. Yeah. So in this sense, the model, yes, this specific result depends on this assumption because you can think of 4 solvers, 2 identical and 2 identical. And then when you do the order by order, you still have maximum amount of competition. All right. So 2 are specialized, so there is a fair point. So that part that says that is always better batching is very much depending on this assumption.
So there's one question from Mo, who asks, is there any consistency constraint on the solver's bids on individual trades versus the batch?
Consistency, no, but the filtering will apply to them as well. So if I propose, if my bid on individual trade is larger than what I'm going to propose to the same trader in my batch bid, I'm going to kick my own batch bid out, essentially. So it's the filtering creates this consistency requirement.
Okay. So I want to be mindful of time. We're almost at the end of this. Are there so there's a question, generally speaking, will you make these slides available? I mean, we have, so just for everybody's benefit, we obviously put the presentation on YouTube, but is there, can you make the slides available?
I'd be happy to make the slides available. I don't know where, if there is a way to make them available on the website
we can probably put them on the website from SIBA. So are there any other questions here? Okay, I see no raised hands. Oh, there's one. Han Chen. Hold on. Are you allowed to talk? I'm going to allow you to talk. Here you go.
Thank you for the presentation. My last question is about is there a way to eliminate the impact of gas? Because it can change, like it's just based on the network condition, and when the orders are matching, the price can be different from when the order is executing on chain.
So eliminate, what do you mean eliminate?
I just don't know like how to solve this challenge. Like if the gas price can change based on the network. If the network is busy, the gas fee is higher, and also based on the token price, right? If the token just get more expensive, then means the processing cost is higher.
Yeah, so this is all on the solver shoulder. They bear this risk and they have to figure it out. Of course, they can revert. That's what I was discussing earlier. So in practice, they can just then, that transaction might fail. But if it doesn't, what they announced at the bidding stage is what they need to deliver. So it's really about pushing to the professionals this complexity, which is, okay, gas might change, prices might move, many things might happen on chain from the time where you submit your transaction to where it actually lands.
Okay, so there's one more question in the Q&A from, oh, sorry, Dehan. Sorry, you were talking.
No, I just want to say thank you. Yeah.
Oh, okay. Yeah. Okay. There's one more question from Daniel in the Q&A, and that's the last question because we're out of time. So is the ability of solvers to dominate going to be different in batch versus order by order?
To dominate?
Yeah, I think with the heterogeneity, I think there is no dominant player here, right? Like one was bit higher, stronger bidding power.
I don't know. Maybe so there is a sense in which if you are competing in a batch auction, you probably want to be able to cover more ground in terms of type of orders. Whereas if you are competing in this order by order auction, you can be able to maybe specialize more. I don't know if this is what he hints at. That will be to some extent correct. And of course, in this yeah, I mean, I don't know. Let's say I don't know, possible, but
yeah, okay. So he agrees that it was thinking of a particular solver strategy.
okay. Yeah, it's not part of the model, and in practice there is quite a bit of overlap between solvers on competing in batch auction and solver competing in other auctions. So maybe it's there, this tension, but I don't quite necessarily see it very much in practice. Okay, that's my.
Okay.
And if anything, Cow protocol, which is the one that runs the batch auction, has way more solvers than all the other protocol, and which will indicate perhaps even more specialization there. But then there are many things like the subsidies are different, what the protocol pays is different. So it's maybe not just the auction mechanism itself.
Okay, well, so thank you so much, Andrea, for a very insightful presentation here. I think we all benefited from this.
Thank you,
let me just
Andreas.
quickly, so to the very end, let me just quickly plug our next symposium webinar, which happens 2 weeks from now, where we're going to talk about MEV or MEV, maximum extractable value mitigation strategies. We have Siamak Banabi from the Ethereum Foundation and Shay from Flashbots there to talk to us about what's currently in Stack. And as you can all see, anything related to DEX trading is now really becoming a very big research area, simply also because there's novel mechanisms and novel institutions. So this is exciting work. And Andrea, I really appreciate you contributing to our collective learning and understanding here. So thank you for that.
Thank you. Thank you for all the questions.
All right, that's it. Thank you so much, everybody. Bye-bye.